Awesome. Cool. Yeah, so I sent out the slides and hopefully you guys will find that helpful to have them ahead of time. And hopefully they've been helpful in general. My intention with them is to sort of, at least with the worked examples, make sort of the hardest problem you can see. So maybe just to introduce a little bit more variety than what you'd see with long kappa problems or with the Canvas problems. But hopefully my intention is that if you can go through those problems and say you understood every step, then you're in pretty good shape for that concept. So yeah, like Tyler said, feel free to follow along and let's get started with the Biot-Savart law. Let me share my screen. And let me switch to a different tab. This one. Okay. Yeah, so block 3, it's all about magnetism. So in block 1, we learned that stationary charges produce electric fields. And in block 2, we sort of learned what moving charges are. That's just current. And in block 3, we introduce a whole new different type of field. We learned that a moving charge produces a magnetic field, whereas a stationary charge produces an electric field. So it's a whole new realm. But that being said, there's a lot of similarities. And that sort of starts with the Biot-Savart law, which just reads that dP is equal to mu naught I dl cross r over 4 pi r cubed. And this is strikingly similar to Coulomb's law from block 1. It's sort of just a formula for building up a differential piece of magnetic field from its constituent components. And in fact, just like Coulomb's law depends on some amount of charge, the Biot-Savart law tells us that you won't have any magnetic field without some moving charge, without a current. But it's a little bit more complicated at the same time. You have a cross product that you didn't have in Coulomb's law. You have the dl, which represents some infinitesimal length along which you're moving. And you have the r vector, which points the same from Coulomb's law, which points from your source to your observation point. So it'd be pointing from whatever's producing that magnetic field, whatever is carrying the current, to wherever you want to observe. And then little r is just the magnitude of the r vector. I don't think there's too much else to say about Ampere's law, or excuse me, the Biot-Savart law. I would say if you want to vote on it in the examples down the road to see a worked problem, we have one. But we wanted to keep it sort of more streamlined this time and not sort of jump around. So I think I can hand it off to you, Tyler.
Awesome, thanks, Nick. You can hear me, right?
Yeah.
Cool. All right, can you, let me just allow myself to share my screen. Why don't I just do that? Can you stop yours real quick? Thank you. All right, sorry guys, kind of jumping around a little bit here. We had to toss together some last minute plans, so I apologize, but it'll be me for the next few minutes, so don't worry about it. All right, so I can see that on my laptop, so I take it you guys can too. All right, so Ampere's law, the block 3, right? This is almost entirely akin to Gauss's law from unit 1, right? So whether or not you hated it or loved it, this is basically the reincarnation of it, right? So where we had Gauss's law was the surface integral of E dot dA equal to Q enclosed over epsilon naught, right? Now we have the path integral of B field dotted with differential length is equal to mu naught times the current through that loop, right? So altogether, very, very, very similar to Gauss's law, right? In fact, the process to solve the problem for B field is almost identical, right, to Gauss's law, right? I would recommend solving for your through current first, right? Because that's going to be very, very similar to your enclosed charge from last time, right? And that depends on whether or not your charge density, or sorry, your current density, excuse me, is constant or non-uniform or uniform, right? So remember we had charge densities, right? They could have been either, dq could have, rho dV or sigma dA or lambda dL, something like that. Right, with current, the nice thing is we only really have one possible format to deal with, and that is this down here called JDA, right, where J is the current density, right, current per unit area, right? So to solve for actual current, right, we would take the integral of that current density dotted with the differential area vector, and that would give us the value for the current through our Amperian loop, right? So I would recommend starting here every time, right, just like we did in Gauss's law, because this will be most, if not all of your work, right? Remember, we never want to integrate this left-hand side of Ampere's law, right? Because we can't take that integral straight up, right? Those symmetry arguments from unit 1 we have those two vectors are parallel, right? B must be parallel to DL to start. And then 2, B must be constant, right? Those two symmetry arguments still apply, right? In exactly the same fashion in unit 1, except the only difference is, well, I've got an area in unit 1 and a differential length in unit 2, right? So, or in unit 3. So a little bit different to think about, I guess, conceptually, but the same arguments apply, right? Those two vectors have to be parallel and the B field has to be constant everywhere within the loop, such that I can get this simplification, whoops, not A, B times L there, right? And that is the way I would solve an Amperian loop problem, right? I cannot take this integral straight up, right? I don't know how to take the integral of a dot product, right? So make sure to simplify that and get it down to B times L. That is something workable for us. And then like Nick said here in the notes, please don't worry about displacement current quite yet. That's Maxwell's addition to this equation, and we'll actually touch on that next week in unit 4A, right? So don't worry about that quite yet, just mu naught I through for this unit, right? So that being said, move on to the next slide here, right? So got this lovely image here, right? So first things first, so Ampere's law is a law of nature, right? So it holds for any closed loop, right? What we mean by that is any loop that takes any, well, closed shape, right? So I mean, for whatever reason, if we wanted a, triangular loop, cool, right on. Right? If I wanted a, a square loop, sure, go ahead, right? Any loop that is closed, Ampere's law will hold for, right? The only caveat is it's not useful for any loop besides a circular loop because we can't apply the symmetry arguments that we could before, right? So it's useful in specific situations, but that's not to say that it doesn't apply to multiple current loops, things like that, right? But so this is just a visual down here of what the B field made by a current carrying wire would look like, right? So, excuse me, I know it's kind of hard to see, but this wire is coming out of the page at us, right? Current carrying wire, right? And we know from the right-hand rule, right? I can just take my thumb, point it in the direction of the current, and my hand will curl around the wire in the direction of the B field, right? So in this case, I've got thumb out of the page or towards me, and then my finger is curling in a counterclockwise direction, right? That would give my B field that same counterclockwise direction, right? So something like that, if I could draw decently, right? So yeah, that's what this image is trying to show you here, right? Kind of a cool little interactive image here, but yeah, that would be the B field made by a current carrying wire for the current coming out of the string, right? So I see a question here, right? Ampere's law applies to circular loops. So I say good question. So Ampere's law, I believe it's actually stated right down here. Give me a second. No, sorry, going too far. Ampere's law applies to any closed loop, but for the purposes of this class, using your symmetry arguments, it's only useful for a circular loop, right? Because think about this for a second. If I had a square loop, right, my B field and my differential area vectors, or my differential length vectors, my apologies, are not always parallel at every stage along my loop here, right? So a shape like this is not really super useful to me in this class because I can't make those symmetry arguments and I can't reduce the integral, down to B times L, right? And if I can't do that, I can't solve for B field, right? Which is a moot point because that's what I'm actually looking for, right? So if I can't simplify the integral, in other words, it's not really super useful, right? So Isaiah, does that answer your question? Cool, thank you so much, appreciate it. All righty, so very good question, but moving on to the next image here, right? So here's that aforementioned square loop I was talking about, right? So again, value of the integral is the same, whether the Amperian loop looks like a square, a circle, a triangle, anything, right? It's just we can't solve for the B field in any of those situations besides the circular loop, right? So I believe that's stated a little bit further down, right? Right here, yeah, there we go, right? True always, but only useful sometimes, right? And so what we mean by that is it's useful in terms of circular loops, right? Again, because of that nature of those B field and differential length vectors, right? So that was all that to say that when you got a circular loop, life is good, right? When you got a square loop or triangular loop, yeah, not so great, right? So just pay attention for those circular loops. I would be shocked if they, tried to, confuse you by anything else. But just so you know, when you can and cannot use Ampere's law, right, is when you ask for B field anyway, and you can't make those simplifications, right? Then you can't really use Ampere's law for this class purposes, right? So remember, I need to get to here, right? That is my check, B times L, okay? All righty. So this is kind of restating basically what I have said already, but these are the two symmetry arguments that we learned way back in unit 1, right? And they still apply here, right? So first simplification is to, again, make sure these vectors are parallel with one another. If they're parallel, right, the dot product of two parallel vectors is 1, right? Or the cosine of 0 is 1, right? Either way you want to look at it, right? I have to get rid of that dot product first, right? That is step 1, right? I find that most students seem to remember this step down here, right? Removing b from my integral, right? But I can't do that first, right? I cannot pull a b-field vector away from a dot product, right? That's not how math works, right? So I have to simplify the dot product first, and then I can take the b-field out of the integral, right? Only in those two in that order, sorry, only in that order. And if this was a free response question, we could very well ask you those two symmetry arguments, right? So just remember the order of those two and what the effect they have on the actual process, right? So if you have any questions about that, feel free to let me know. But other than that, I feel like from unit 1, those are pretty well hammered into your head by now. All right. So on to our next topic, right? Onto magnetic flux, right? So basic definition of that being the integral of the b-field vector dotted with the differential area vector. Right? Hopefully you all are very, very familiar with this because it's what Faraday's law is built off of, right? And then as a stipulation, right? If the surface is completely closed, right? Meaning, you know, I mean, it's a closed shape, you know, got a circle or whatever, right? Then this integral holds true, right? The surface integral b dot dA, that flux through there will be 0. And the reason for that, right, is given in this paragraph down here, but what this looks like as far as a picture is concerned, right? It says that we're not allowed to have a north pole by itself generating magnetic field lines. And what we mean by that is that whenever I have a bar magnet, I've always got a north and a south pole, right? It's illogical and incorrect to say that I've only got a north pole somewhere, right? Because that's not the case, right? For every magnet, even if I made it really, really small, I still would have a north and a south pole, right? No matter how many times I cut it in half or anything like that. All right, so what this is saying is that the north pole is going to generate your magnetic field lines that go back towards the south pole, right? So there's no similar to, or unlike where we had charges in unit 1 where I could just have a positive charge that would make E field lines, right? What we're trying to say here is that B field lines come as a result of a magnet, not just but just randomly just by itself, right? So I've got to have some sort of bar magnet or, you know, some current carrying wire, something generating this magnetic field, right? So that's what this slide is sort of getting at, right? Surface is completely closed, then this is equal to 0, right? But more often than not, we will ask you for the magnetic flux in terms of Faraday's law, right? And that is usually not 0, it's some sort of B times A quantity, right? So we'll get to that later, but we wanted to be for correctness sake on there. So on to topic, right? We had magnetic forces, right? So remember that there are two equations for magnetic force, right? Both very useful in very specific scenarios, right? This is the first of two, right? So this is the force exerted on a particle of charge, right? Moving with some velocity in some magnetic field, right? So notice how this force is not differential, right? It's not differential, right? This one is given to us straight up, right? There's no integration required with this magnetic force at all, right? It's just going to be QV cross V. And this comes as a result of if I just have some magnetic field in some region, right? I'll say I've got a B field pointing to the right here, right? Hopefully this question looks a little familiar. But if I had a charge in, here, moving velocity like that, right? I would have a magnetic force exerted on this particle, right? Because my velocity and B field vectors are perpendicular, right? I would have just a circular force, right? So the particle would move in a circle, right? Into the page, something like that, right? So yeah, most important thing to keep in mind is that if my velocity is 0, right? But if the particle is not moving, right? Then I will not have a magnetic force, right? It has to be moving in sort of mathematical perspective, right? Looking at QV cross B, if V is 0, well then 0 cross V is going to be 0, right? So make sure that when you're asked about magnetic force, right, for a particle, that particle better be moving, right? And then the last thing I want to cover with this specific slide is that Q, right, is the charge on our particle, right? Keep in mind that the charge on a proton is positive, right? And the charge on an electron is negative, right? So for any situation where I have a proton, I can do the right-hand rule as normal, right? Life is good. But if the situation says I have an electron instead, right, then I can still do the right-hand rule as normal, but I have to remember at the end what I do is basically grab my thumb and rotate it 180 degrees, right? It's got to be the opposite direction of whatever I found out for a proton, right? Again, because that charge is negative. Right? Do not forget about that. There's a question called like electrons moving through a television tube or something like that on your review or on your guys' sets of long kappa problems. that's the one I'm talking about. In this question, that question comes up a lot on almost every exam I've seen, right? So they will try to get you because they will say electrons, right? So just keep in mind, QV cross B, Q is negative, you got to flip your sign, okay? That's all I have to say about that for this slide here. But now we've got just a quick little demonstration of the right-hand rule, right? So this is super hard to see over camera, so I'm gonna try my best, but we're gonna go from here. So how I do this, right? And it's been written out there for in front of you. So we have basically three quantities we have to worry about, right? We have the velocity, we have the B field, and we have the force, right? The force is always the last thing, so I wouldn't try to mess with that first, right? So I would start with the velocity first. I always think of velocity as my index finger, B field is my middle finger for biggest finger, right? And that way my thumb will always point in the direction of my force, right? Always. So let's just do a random example. Let's say I had B field into the page. I had velocity moving to the right, right? What direction would my force be? Well, I will do my middle finger first, B field for biggest finger. So I'll point it into the page, right? Velocity would be index finger. So it's going to go right. And that means my thumb, right, will point in the direction of my magnetic force, right? Which would be up on the page in this case, right? For a proton. Apologize, I did not now specify that, but for a proton, let's say Q is equal to positive Q. All right, for a proton, it would be up on the page. Right, for an electron, right, say Q is equal to minus Q, so we have the same situation, B into the page, velocity to the right, what direction would F be? Whoops. Now, I could either look at my work from last time, or I could just do it again, it's totally fine, right? B field into the page, velocity vector to the right, thumb would normally be pointing up on the page, right, but because I've got an electron, that Q is a negative sign now, right, so this sucker becomes negative out here, right? That means I basically just grab my thumb and rotate it 180 degrees, such that my force now points down on the page, right? So that's the best I got over a camera, but hope you realize the difference between having an electron and a proton, right? Either way, your force is going to be pointing up or down on the page, like I said, depending on what charge you've got. So just pay attention, right? Because that's one of the ways we can get you on an exam. So just pay attention to that. All righty. So this is some more examples here, right? I already did a couple, so I won't do that one. Something I kind of covered a little bit earlier, but in general, the force exerted by a magnetic field on a particle is a centripetal force, right? So hopefully from Phys 1, that definition sounds a little familiar. It just means that it's going to move something in a circle, right? Centripetal force points always inwards towards the center of my circle, right? So the effect of a magnetic force affecting a positively or negatively charged particle, right, is just to bend it in a circle, right? Let's see, yeah, cool. I'm sure the next question in mind is, well, what happens when I've got, a helix, or how about, right? That's what we're trying to cover here. So I get a circle if and only if V is entirely perpendicular to B, right? So my velocity vector and my B field vectors are entirely perpendicular to each other, right? Then I will get a circle. Right, I'll just write an arrow on the circle here. Right, just due to the nature of a cross product, right? The cross product of two perpendicular vectors is 1, right? So if I have V and B are automatically perpendicular, well, then I'm just going to get a circle out of it, right? Nothing fancy there, right? The centripetal force will be pointing towards the center of the circle, and I will get a circular path out of it, right? But now this situation says, well, suppose I have some component of velocity that is parallel to the magnetic field. So let's say, right, if that's my B field there, say my velocity in purple here is, well, now it's off at some angle, right? That should look a little familiar. It was a studio example based on this. But notice how that velocity vector is not entirely perpendicular nor parallel to the B field, as in it has two components, right? So we can cover the perpendicular one first, right? Perpendicular component we know is just going to result in a circle, right? The effect of a velocity vector perpendicular to B field in any way is just to move the particle in a circle. All right, so we got that, right? We're good there, check. Right, the parallel component, however, right, is unaffected by my magnetic field, right? Because two vectors that are parallel, right, obviously their cross product would be 0, right? So in terms of this formula up here, right, if V is if I have a component of V that is parallel to B field, right, that will not affect my magnetic force at all, right? And as a result, it's just going to stay constant, right? So in this example right here that I just drew right there, right, I would get a helix out of this, right? Because I've got a circle from the perpendicular component, and I've got, well, nothing here. I'll just put an X. I've got nothing here, right? So that is unchanged. That means that my circle will be a moving circle in the direction of that parallel component of velocity, right? So it would look, if I was looking from this left side, if I was looking at this particle's movement, I would see a circle, right? But if I was looking, straight on like I am right now, I would see a moving circle, right? As the X component of that velocity is unchanged, right? So all that's to say, helix if you've got two components, right? Circle if it's only perpendicular, right? That's how I would sum that up. So a lot of words, but that's how I would sum that up. I would be surprised if there wasn't some sort of multiple choice question based on something to that effect, right? But that's all I will say about it for now, right? That's all these paragraphs are saying, just a little bit more elegant language. So feel free to read those if that didn't make any sense. Other than that, looks pretty good there. Yep. So here we've got just the illustration of what that helix would look like. Again, that force is, well, still going in the centripetal direction, right? Straight to the center of the circle. But notice I have two components of velocity, right? Perpendicular one like I expect, right? And the velocity is unchanged, or the parallel component of velocity is unchanged. So notice how this circle keeps moving up and up on the page, right? Because this component is, again, unchanged by my magnetic field, right? So it's just going to keep on going, right? So I've got my circle just continuously moving up and up and up and up in a tornado twister-like fashion, okay? Sounds pretty good, okay. Yep, so this is just a summary. Again, charged particle moving in a magnetic field will travel in a circle if its velocity is strictly perpendicular, right? Helical trajectory, if I've got both, right? I've got a V parallel and a V perpendicular, right? And then completely parallel, right? I've got nothing, right? No force on the particle, right? No force. Okay, so that's a nice little summary slide there to read just before you go into the exam if you can't help remembering, something like that. But that is about all we have on QV cross B, right? Now, well, actually, I should probably go over this as well. One important thing to remember about charges moving in a circle, right, is that there is no work done on them. So as in magnetic fields do no work on those free charges that we're talking about, right? So this is a sort of mini proof as to why we don't get any work in the first place, right? So remember, recall the definition of work from Phys 1, right? The integral of a force dotted over some length, right? We've already established that our force is QV cross B, excellent. And then the differential length, right, is in terms of velocity, right? Because velocity is in terms of meters per second, right? So if I multiply that by a, well, change in seconds, right, I'm just going to get meters out of it, or distance, right? So I could change dl into just v times dt, excuse me. And then we can make those substitutions back into our work formula. We'll get something that looks like this, right? But unfortunately, right, if V is perpendicular to B, as we said down here, right, we will end up with no work, right? Magnetic field cannot alter the kinetic energy of a free charge, right? Since the work energy theorem starts that, yeah, change in energy is equal to work, right? So follow that mathematical proof if you're very curious as to why we get no work. But in summary, things that are moving in a circle, right? No work, right? No work, no change in energy, no change in speed, none of that stuff, okay? All righty. So like I mentioned before, where we have two formulas for magnetic force, right? That first one was just for a charged particle, right? And usually it's fairly obvious which one you'll be using, right? It'll either say some proton, some electron, something like that, or it'll say, hey, I've got this current carrying wire, right? Or this slanted wire, something like that, right? So it's usually pretty obvious which one you're going to end up using, right? And really, I guess the main thing is, well, do you have a velocity or do you have a current or do you have a length, that sort of thing, right? It becomes very easy to tell which one you should use in different scenarios. But notice how this second formula for force is in a differential form, right? So you know what differential forms mean? It means you're going to have to take an integral eventually, right? Because we are integrating over an infinitesimally small part of that wire, right? As we move along, it's either its length or its height, something like that, right? We will have to add up all of those components of the force as we go along, right? So don't forget that is a df, right? I'll see a lot of people writing IL cross B, right? And if you're lucky, it does simplify down to this sometimes, right? But you can't start here, right? Don't start there, right? Always start at the differential form, right? Because if you're lucky and everything's constant, then you can just, well, integrate a DL, for example, and you'll just get an L out of it, right? So just be careful. Don't make those assumptions too early, right? Until you're absolutely certain that things are constant, okay? So, but differential force is equal to I, the current, times DL, the differential length, crossed with our magnetic field vector. Right, so it looks somewhat similar, right? It's only 3 variables, right? But not QB cross B, we have I DL cross B, all right, where DL is an infinitesimal segment of that wire, right? So a little different than QB cross B necessarily, right? You'll usually be asked for, hey, what's the DL vector, right? For example, write that out, right? And then the B field vector is usually given to you. It's like, it'll be like B naught X J hat, for example, something like that, right? That's usually given to you. But the differential length is something you usually have to come up with, right? And I find it, as a hint to you, I find it kind of helpful to start with a length vector first, right? And then take a derivative of that to get to differential length, right? My mind doesn't work super fast in the sense that I can't get this right off the top of my head. So I like to start here and then go down to differential length. So if that helps, go right ahead, right? Remember, length is just how I describe how I get from the origin to any point along my curve, period, right? So I find that length is a little easier to start with and then moving forward to differential length. But to each his own, totally fine, but that's how I would start my problem if I were you. Okay, the last thing I have to talk about here is magnetic torque. Right, so from Phys 1, I'm not gonna lie, torque was my least favorite topic. I really did not like torque, but thankfully in Phys 2, it's a little bit more straightforward, mostly because we have a different definition for torque now, as in something that's a little bit more useful to us when it comes to magnetics, right? So here's the main one from Phys 1, right? You have a radius crossed with some force vector, right? You usually were in Phys 1, you were talking about some like seesaw-like thing, for example, right? Something on a fulcrum, and you had a force here, right? This is the torque situation you're used to dealing with in Phys 1. However, in Phys 2, we push that a little bit further. We say now we're going to have some sort of magnetic force acting on, well, maybe some sort of current carrying loop, something like that, right? And if that's the case, this relationship still applies, right? I could just do my DF formula would still be IDL cross B. Or, right, I can scroll down here just a little bit, right? And look at this relationship called the magnetic dipole moment, right? So why it's called magnetic dipole is not super important to you guys, but just know that it's given by the symbol mu, right? And effectively is equal to n, the number of turns in your loop, times the current in your loop, times the area vector of that loop, right? So again, this is what you might think it's useful for torque on a current loop, right? Not a wire, right? Current on, or torque on a current loop, right? Very different things, right? And then if that's the case, well, I know that torque is just mu, magnetic dipole, crossed with our B field, right? And more often than not, this is a much easier cross product to take than R cross F, more often than not, right? And usually it's because this area vector and this B field vector are already perpendicular to each other. Again, more often than not, sometimes it happens we have to toss a sign in there, right? But more often than not, those are already perpendicular to each other. So you'll end up with NIAB fairly often. Whoops, sorry, I can't really see that. Not fairly often. But again, make sure, don't always just assume that, right? But make sure that those vectors are perpendicular to each other. And if they are, you can just multiply them together, right? So that's pretty much all I can think of for torque on a current loop there. We can do some of those examples if you guys have any more questions about that. But at this point, I think, yep, we'll transition back to Nick. Our apologies, right, to talk about Faraday's law while I get some water and a break. Cool. So Nick, I will toss it back to you.
Thank you. Wait, there's a question. Doesn't A have to be per? Okay, if you want to.
Yeah.
Go ahead.
No, you're good. Yeah, Isaiah. So I apologize. I might have misspoken and said parallel. I apologize if I did say that. But using magnetic torque, or yeah, the torque for on a current loop, right? Mu crossed with B would be NIA cross B. So A has to be perpendicular to B, right? Or they have to be some angle between the two. So I could just multiply by sine of theta, for example. Does that answer that question? Cool, awesome. Thank you for asking questions. Yeah, again, guys, please, if you have any questions, please feel free to ask. Right, no big deal. All right, Nick, sorry, it's all yours.
No, you're good. I'm going to keep my video off because it's going berserk for some reason. But
yeah, I noticed that too.
Yeah. Two quick things to add. Yeah, I thought that was an awesome explanation by Tyler. But if I share my screen real quick, just two quick points that often confuse people. The R in the torque equation I can't remember if you mentioned this, it's not the same R that we use in Coulomb's law, or in the Biot-Savart law rather, in block 3. So in torque problems, or I guess Tyler, if you want to elaborate on this, I can give the floor to you.
No, I mean, go right ahead. I forgot
Okay.
about it. I talked about it last semester and totally forgot this
No,
semester.
you're good. You're good. You're good. Yeah, just to be super duper careful, because the torque vector, when we're dealing with it in block 3, that's the vector that points from the axis of rotation, maybe from the x-axis or whatever, to the point where force is being applied, and force is usually being applied on the wire as per the equation dF equals IDL cross B. Whereas in Biot-Savart law problems, for instance, in this one I have right here, the R vector is something different. The R vector points from a source, whatever's creating some sort of magnetic field, to an observation point. A little bit different there. And just one more quick point of caution. I do like the formula of magnetic dipoles. It does make things a lot easier, but it only applies to closed loops. So for instance, if I just have a straight wire floating in space, I'm going to have to start with the fundamentals. D tau equals R cross dF, and I can't make a loop out of just a wire. I can't like pretend the current's going down or anything. But other than that, awesome. We can move on to motional EMF. Oops, wrong thingy. There we go. Okay, so motional EMF is where block 3 gets really interesting, in my opinion. It's where rather than just electric fields or magnetic fields just sort of existing in space, maybe we can sort of tell where they come from Gauss's law or from Ampere's law, but it's a way to generate one from another. It's a way to get an interplay between electric or magnetic fields. So let's look at the mechanics behind this, of how the motion of charges through a magnetic field can induce an EMF. So let's suppose I have a conducting bar and it's moving with velocity v in the presence of a magnetic field. If it's moving in the presence of a magnetic field, well, there's charges in this magnetic field. So Tyler already talked about the equation F equals QV cross B. So what's happening here is, if I get a draw, we have all these charges, negative and positive, and they're going to be in this metal rod. Doesn't have to be a metal rod, but metal rods are great. And if that metal rod is moving with this velocity perpendicular to the magnetic field, it's sort of moving out of the page that way, those charges just by themselves are going to be moving perpendicular to a magnetic field. And we already know that when a charge moves perpendicular to a magnetic field, it's going to be subject to a force. So what's going to happen is, let's say I have positive charges. A positive charge, according to this equation, if I make my index finger the green velocity vector, and I make my middle finger the blue magnetic field vector pointing down, I like Tyler's analogy of big for middle finger, since that's the longest finger. The force, which is your thumb, that's going to point towards one end of the rod. So the positive charges are going to be pushed towards one end here. And what that's going to leave is a residual negative charges here, which is pretty cool on its own. But what do we know about from block 1 when we have charges separated like this? Well, if we have charges separated like this, if we have some positive charges on one end of the rod and negative charges on the other, whenever we have positive and negative charges just separated, there's going to be an electric field pointing from the positive charges to the negative charges. And this is really where we get to see the interplay between electric and magnetic fields. So on the one hand, we have the motional EMF, which is causing a magnetic force pushing positive charges to this end of the rod. But at the same time, they're balanced. They're balanced by an electric force that's pushing them towards the other end, because electric forces always push positive charges in the direction of the electric field. So there's sort of an equilibrium established, because the positive charges, on the one hand, they're going to be pushed towards one end of the rod from a magnetic force, and then towards the other end of the electric or towards the rod from an electric force. And since you have that equilibrium, we can equate those two forces. So this, of course, is just the magnetic force. And this is the electric force. Force electric. The Q's obviously cancel. And we get this relationship that's going to come up again and again. And you'll see it even more in block 4. E is equal to V cross B. Oh, excuse me, E equals V times B. And what this tells us is that if I have an electric field, that sort of insinuates a voltage. After all, I know from block 1 and 2 that I can just integrate along an electric field to find what my voltage is. So I can just integrate this electric field because I know what it is. It's V times B. And integrating across the length of the rod gives me V times B times L. Let me check the chat for questions, if there are any. Shoot, it's not letting me. Okay, just speak up if something I say doesn't make sense.
Nick, I see one. Question is the small v in E equals V times B voltage or velocity?
That is going to be velocity. That's the velocity at which the rod is moving, because that's the velocity. Let's keep things consistent with colors. That was that green velocity that the rod was moving with. And it's that green velocity because those little charges in the rods, the whole entire rod is moving with that green velocity V. So those individual charges are moving along with the rod with that little velocity V. So this is the little velocity V in my E field expression, and then I can integrate my E field to find a voltage. So big V for voltage is equal to little b velocity times B field times L.
Yep, you're good, Nick. He
cool.
said that answered his question.
Yeah, I wish I wasn't a boomer and could figure out how to get to chat, but whatever. Let's see what else. Okay, so that's motional EMF. And oh, here it is. I'm just goofy. Awesome. Okay. All right, so Faraday's law. So real quick before I move on to Faraday's law is, although we talked about induced voltages with motional EMF problems, these aren't Faraday's law problems, and you shouldn't try to apply Faraday's law in these problems. I'll show why further on down the road, but what it boils down to is that with a rod, for instance, or something else moving through space, you can't define a closed loop, and Faraday's law depends on having some sort of a closed loop, which brings us nicely to Faraday's law. So if you just straight up look on your equation sheet, Faraday's law is going to be this big, scary expression. It's going to be the closed loop integral of the electric field plus the velocity crossed with the B field dotted with dl. That's somehow equal to the negative derivative of whatever this is. Maybe that's sort of looking like flux. I remember definitely being in Phys 2 and looking at Faraday's law on the equation sheet, and it was absolutely scary for me. So hopefully in a few minutes, I'll show you that it doesn't have to be too scary because we can just break it apart. So let's start with the right-hand rule. The right-hand rule of Faraday's law has the time derivative of magnetic flux through some surface. So Tyler mentioned earlier magnetic flux. We can just define that for any surface. If I have some surface, maybe it has an area, and there is a magnetic field going through that surface, that's enough for us to give a flux, because flux is nothing more than the integral of B dot dA. Yeah, that's all Faraday's, the right-hand side of Faraday's law is. It's just the time derivative of that flux. Is that flux changing with respect to time? That could mean either the B field is changing with respect to time or the area. But again, it's just any open surface has a flux if there's a magnetic field going through it. And we're interested in the time derivative of that flux. Now, the left-hand side of Faraday's law is a little bit less useful for Phys 2 purposes, but we can still look at it and it's still instructive. It's a closed line integral. So kind of like Ampere's law. Ampere's law is also a closed line integral because in Ampere's law, we had the closed line integral of B dot dl. Faraday's law is a little bit more than that. It adds to that. It has the closed line integral of just the E field dotted with dl. And then there's V cross B, the velocity crossed with the B field term. And then each of these terms by themselves, they have their own meaning. So for instance, the E dot dl term, this term just tells us that integrals of curly electric fields, and those are really just, that's just a fancy way of saying electric fields that are produced by changing magnetic fields, give some voltage. If I think back to block 2, integrating an electric field over some length gave me a voltage. This just tells me that if that electric field happens to be a curly electric field, I'm going to get a voltage. I don't remember how much we stressed this in block 1, but something we did stress in electrostatics was that for a static electric field, or not a curly electric field, sometimes it's called a conservative E field, you can never get a non-zero value for this integral. If you integrate around a closed loop, you're always going to get 0 in electrostatics. But now we have curly electric fields, non-conservative E fields. Those can give us voltages. And then this other term, the V velocity cross B field term, that term just tells us that the motion of the loop itself. So in this case, this would be the velocity of the loop, the velocity of the charges in some sort of loop that's moving, also creates voltages. So for instance, for those of you who were here for the topic 3E studio, when you wave those coils near the magnets and you got the galvanometer to move, that's what this term was doing. It's just telling us that we can get some voltages if we're moving, like imparting velocity with our hands in the presence of a B field on some loop. But if we look at both of those at the same time and combine them, it doesn't matter whether those voltages come from moving a magnet from a near a stationary loop or moving a loop near a stationary magnet. It doesn't matter whether it's this term of the left-hand side or this term. Either way, those are induced voltages. So really, the left-hand side of Faraday's law is just EMF, the induced electromotive force. And so we can express Faraday's law in the much simpler term that we're used to. It went from this big, scary equation on the equation sheet, and all we have to worry about is the EMF is equal to the negative integral, excuse me, the negative derivative of the magnetic flux. That's all we have to worry about. Yeah. Whenever Faraday's law changes for, or excuse me, whenever the magnetic flux through an open surface changes for any reason, there's going to be an induced EMF. So for instance, if I'm dragging a loop through a magnetic field, the flux through that loop is changing because that loop went from a region where there was a magnetic field to one where there wasn't. So you have a changing flux and therefore a EMF. There's a chat question. Why is the big equation representing a closed surface integral while the other one is open? Lisa, did you mean this question where one side is a closed loop integral and the other is just the, yeah. So the reason why, shoot, I can go into this, but the reason why is it boils down to, for those of you who had Calc 3, if you have an electric field, you can take its curl, and that's equal to the negative time derivative of the B field. This is known as the integral, or excuse me, the differential form of Faraday's law. And this is really a more point-like representation of where electric fields come from. In fact, this tells us that in order to have a curly E field, an electric field that's non-conservative, there has to be a changing B field. But the reason, or how we got from here to here, is through Stoke's theorem. So the way you convert from differential forms of Maxwell's equations to the integral forms is you integrate both sides over a surface. So we have the surface integral of E dot dA is equal to the negative flux, because that's what the integral of the B field dt is. So this right-hand side is already simplified to flux. But then for those of you who had Calc 3, if you haven't, Stoke's theorem is coming up. Stoke's theorem basically tells us that if I have a curl and I'm taking an area integral, I can convert it to a closed line integral. It's definitely way beyond the scope of this too, but I like where you're thinking. Does that answer the question?
Yeah, thanks.
Of course. Yeah, no, that's a great thought. Cool. Yeah, awesome. So we were here. We said that a changing, or rather dragging this loop through a region where there was a magnetic field into one where there isn't, induces a voltage just because, well, there's a changing flux through that loop. But conversely, you don't have to move the loop. You can have a stationary loop and then just increase the magnetic field with time. If the magnetic field is increasing with time or decreasing with time, as long as it's changing, you're going to have an induced flux. Cool. So Lenz's law is sort of a supplement to Faraday's law. It's, I guess, a conceptual way to explain where this negative sign in Faraday's law comes from, because we rarely ever care about the negative sign. Usually problems ask us for the magnitude of induced EMFs, so we can usually just forget about the negative sign. But that negative sign is just secretly reminding us of Lenz's law. And that's just telling us that whenever you have a thing like a current or an EMF or a B field being induced by Faraday's law, the induced effects will act to oppose whatever changes caused them. And this is probably easiest to see with an example, but for instance, if I have a loop, and let's say I have a B field in that loop that starts pretty small at time t equals 0, but at time t equals t, it becomes a huge B field. What happens is that the change in B field is out of the page. The change in B field is upwards because B went from being small to big. So that's the change in the B field. What Lenz's law tells us is that the induced current is going to have to be clockwise. Because a clockwise current, if you think about the right-hand rule, if I just have a clockwise current by itself, a clockwise current is going to produce a B field that's pointing down. So the induced current is going to have to act in such a way to oppose whatever change caused it. It was caused by an increasing B field out of the page. So the induced current is going to have to be clockwise such that the induced B field from that current is pointing down. We could hypothetically not worry about Lenz's law and just keep careful track of what's happening to the fluxes and the signages of those fluxes and the directions of the EMFs, but that's tedious. So Lenz's law is super duper helpful. Okay, and last big topic, I think, for block 3 was inductance. And Tyler, correct me if I'm wrong, but I don't think self-inductance is usually tested. I think it's you. Go ahead.
No, I was just going to say, no, I would
Yeah,
bet my
yeah.
life that it's not going to be tested.
Yeah. So I don't want to hark on this too much. Mutual inductance, I think, is fair game. And I think that's the one that's easier to stand. But self-inductance and like the homework that's due tomorrow or whatever, where you have LR circuits, we don't see that too often on the test. I don't want to say that and then no one studies it and then it's on the test and then I feel bad, but just keep that in mind. But regardless, let's go over mutual inductance. And the way that mutual inductance, I think I like to understand it, is sort of by analogy to capacitance. So for capacitors, we can say that capacitance is defined as Q over delta V. Or in other words, the charge stored on a capacitor is just some fixed quantity that depends only on geometry and stuff, times a voltage. Well, mutual inductance is pretty much the same thing, except instead of charges and voltages, I have fluxes and induced EMFs, or fluxes and currents rather. So mutual inductance, it's defined to be the flux in one coil divided by the current in the other. You can have mutual inductance between any two pairs of coils. Basically, it's just the quantity that relates or that tells us how the current in one coil affects the flux in the other. And by analogy to capacitance, capacitance is also just sort of like a fixed quantity. It depends only on geometry of the capacitor and stuff. Mutual inductance also just depends on the geometry and orientation of your two coils. but regardless, it gives you a relationship for finding the induced voltages in your coil. Because once you have the mutual inductance, you can just, or I guess rather starting from, oh shoot, did I not write that equation? I didn't. But there's an equation on the equation sheet that, or I guess we can go from here. If I start with the magnetic flux, if I rearrange this equation to solve for flux, it's going to be m times I. This is sort of the analogy to Gauss's law, or excuse me, to capacitors, because I have, instead of charge, I have a flux. Instead of capacitance, I have mutual inductance. It's the quantity that just sort of depends on geometry and orientation. And instead of voltages, I have currents. But Faraday's law, if we think back a couple slides, tells us that whenever I have a flux, I can just take its time derivative. That's the right-hand side of Faraday's law. If I take the time derivative of flux, I'm going to get an induced EMF. That's what the time derivative of flux is. But taking the time derivative of the right-hand side, mutual inductance is just a quantity that doesn't change unless you change like the orientation of the coils. So that's not going to change. We can pull it out of the derivative and we're left with di dt. So it's a really handy way of getting to induced EMFs. You don't need two coils to do this. Sometimes things can create magnetic fluxes through itself. So for instance, if I have the solenoid and I turn on a current in that solenoid, sort of like that, it's going to produce a magnetic field through itself. But Faraday's law tells us that whenever you have a magnetic field, a changing magnetic field through yourself, you're going to have an induced EMF. That's what self-inductance is. So yeah, the B field that the solenoid produces creates a flux through that solenoid. And that flux, again, if I take the time derivative of both sides, I can get to the quantity. The induced EMF is going to be L times di dt. Again, it's just sort of this constant that's out in front of this differential or the derivative of the current. But again, it's not too, self-inductance isn't too terribly often tested. I don't see many practice problems on it. And mutual inductance sometimes is. It helps to know how to apply this formula right here. If I can erase this stuff. This formula is pretty important. How to find the mutual inductance of two objects. Cool. And then the way inductors behave in circuits is that they oppose changes in currents through them. So if I have the induced EMF, as Faraday's law tells us, the negative derivative of the flux, and I just put in the definition of flux, which is L times I, this tells us that a change in current is going to cause the inductor to oppose that change in current. So inductors sort of act like a choke on current. Whenever you have problems, like with when you have switches closing and it says, what if the switch has been closed for a long time or the switch has been open for a long time? The key thing to remember there is that unenergized inductors, when the current turns on suddenly, those act like open switches because we have pretty much an inductor. And you're trying to send a current through that inductor, it's going to choke the current because of that changing flux. It's going to not want to permit that current to go through. But on the other hand, when you have a steady current, when you have something flowing in here through a long time, that's just sort of like a wire. So it's going to be acting like an ideal wire. Cool. I think I put an example about that. And LR circuits, sort of the last topic. They're sort of similar to RC circuits that we did a lot of in block 2. That would be just if I had some sort of inductor and maybe a resistor in the circuit. I can use, in that case, I'd be using this equation because there's no EMF source. So the current or the energy stored by the inductor that would be providing energy to the circuit would run out and the current would decay to 0. Or if I had a battery, the current would reach some final I steady state. Any questions? Anything I said that didn't make sense? Because I'm sure there was something.
Cool. Pretty good, Nick. Well done. All right, guys, at this point, we'll go into examples like usual. So I've looked at the form. By far, the the most popular thing people wanted to see was magnetic forces and torque, specifically the torque problem from the 2017 exam. I think that's the slanted wire. So yeah, we can definitely do that. And then follow closely by the Biot-Savart law, and then inductance and RL circuits is after that. So first of all, Portia, are you there by chance?
Yeah, I am.
Oh, awesome, cool. Would you mind starting off with the Biot-Savart law problem while I go find that that magnetic torque problem? That should be on the same set of slides we sent out, but would you mind going over that one first?
Yeah, for sure. Give me 1 second.
Yeah, no worries. I guess I can just randomly talk aimlessly in the meantime. I guess for those of you that are interested, E-Days, obviously this week, hopefully you've heard about it. One thing I'll just remind you of, you guys need a negative test result from this week in order to participate, so don't forget about that. I just got mine done today. There's plenty of availability. So if you are interested in E-Days activities, please go and get yourself tested, that we can enjoy them all accordingly. Yeah, unfortunately, Portia, that's all I got. So I'm just going to sit here in uncomfortable silence until you figure it out.
No, you're all good. Just the current carrying loop question.
Whatever the, I think that's it. I think
I
whatever
sent
the
out
BS
one of my current
is.
carrying loops. Yeah, I can resend it if you're
No, I found it.
cool.
So
Cool.
let's do that. So share.
All yours.
There we go. Can everyone see what's happening?
Yeah, you're good, Portia. I can see it.
Okay, so for this one, we have a, we know that we have a loop with some given radius that has a current in it. And so we want to find the magnetic field at some point P outside of the loop somewhere. In this case, it is on the, can you see my mouse by chance? Sometimes it works and sometimes it doesn't.
Yeah, I can see it.
Oh,
Looks good.
cool. Yeah, so at some point P, and in this case, our point P is on the axis of our loop in the center. So for this one, we want to, again, like as it says on the slides, we're gonna try building up all of the pieces of this Biot-Savart law. And we know that it's not going to be Ampere's law or anything like that, because we don't have, we're not given a magnetic field, nothing is moving. And so it's those kinds of things are more triggers for using Faraday's law or Ampere's law for other problems. So for here, we can start with our R vector, right? So we know here that our R vector always points from the source, which in this case is our loop, because that's where our current is, to the point where we're measuring. So wait, can I annotate? This is going to work, right? So we want to find it from some point on our loop to, oh wait, that's not going to work. There we go. To the point at which we're observing, right? Oh, it continued to be annotated. Cool. Sometimes I don't know. I'm just as bad with technology as you are, Nick. Yeah, so we know that it's on our z-axis, right? And so here we have our R vector here. And we know to find like the length of our R vector, we can see that it makes this cute little triangle, right? And in the vertical direction, right? And then in our XY plane, we know that it's going, we know that it's the radius of our circle, right? With some theta offset, right? And we know that we can find that using trigonometry, our standard sine, cosine practice, right, that we've been practicing this whole semester. And so we know that our coordinates for our original coordinates are some are cosine theta, are sine theta 0. And we're going from there to the origin, which is 0, 0, some height z, right? So in our, then we can just do our normal subtraction from final to our final minus initial, right? So we can say that our vector here, we have negative r cosine theta, right, in our z direction, or in our I hat direction, negative r sine theta in the j hat, and then just the vertical distance z in our k hat direction. We all good so far? I don't see any chat questions, so I'm going to take that as a good sign. And then we know that in our Biot-Savart we have both the vector form of our vector as well as the magnitude of our vector. So it's pretty easy to find that. We do the square of all of the components here, or the square root of the sum of the squares. And so we get we do a little bit of trig simplification, and we get our magnitude is the square root of radius squared plus our vertical distance z. And so the next, you can do them in any order you want, but that our next step in this case is going to be our dl, right? Which is what we're integrating over. So this is going to be we're going to take our loop, our current carrying wire, and chop it up into an infinite number of little small segments that have this current in it. So since it's a loop, we're not going to be able to use, we want to approximate the loop using straight lines. And we get closer and closer to that as we chop it into infinite segments. So we can use our arc length, right? To do that, we know that for any, well, we know that the radius of our loop is staying constant, right? And it's going to change with respect to theta, how far around the circle that we're going at any given time, right? So, and to do this, we know that we have to do trigonometry again, because it's a circle and it's not as easy as just straight lines, which is unfortunate, but that's okay. So yeah, so we just need to figure out which component goes to which part of our dl vector, the I hat or the j hat component. So the easiest way to do that is if you look at like the endpoints, right? So if theta is, say, pi over 2, right? So up here at the top of our loop, we have nothing in our x direction, right? If we're approximating it, and but we have the distance r in the y direction, right? So we know that cosine of pi over 2 is 0. And then our sine of pi over 2 is 1. So we know that we can, like, by looking at the different points around the circle, we can figure out which trig factor goes with which part of our dl vector. So we know, so from there we can build our dl vector, which is usually, the thing here is that usually it is flipped. So you should double check just in case, but I usually, especially for signs, like the signs of your components, but usually for circles and dl vectors, the x direction is sine theta and the y direction is cosine theta. But it is worth it to check. So from there, we can, our next is our cross product, right? If we go back to our Biot-Savart law, and which this is pretty much just algebra. We have practiced setting up cross products in the past with our I hat, j hat, and k hat components. And then we have our DL vector that we found and our R vector. And from there, it's just algebra to find our cross product here. And here we actually, so we don't care about our I hat or j hat components for this problem, because you can see it mathematically here, is if we wanted to find our I hat component, and we integrate with respect to theta, we do get 0 mathematically, but conceptually, I also like to think about it as like if you have a circle, right, and you're looking at the middle point, you have an equal amount of current on the top and the bottom and the left and the right. I think this is a great picture, right? Because we have, because it's centered around the origin, we have an equal amount on the top and the bottom, which will end up summing to 0 if you do compute all of the components individually and add them up. So we can just, this is also a very nice visual. I think this is why Nick put it in, because you can see that the vertical component is, I really like this picture, Nick.
Thank you.
Did you take this?
No, I didn't. But I think it's just like grains of metal or something inside plexiglass, and they just turned on the current inside that copper thing. So
yeah, so you can visually see that the only component is the vertical one. So now after this, the other way you can figure it out is that we also know we can use your right hand rule, right? Using our fingers curling around in the direction of the current, we know that we are going to get a current in the vertical or the k hat direction rather than anything else. So from here, we have figured out all of the individual components of our Biot-Savart law. We found our DL and our R vector and the magnitude of our R vector. And we did our cross product despite all of the nasty algebra. And now we can just plug it into our integral and do the integration. We have to find our B field here. We can integrate around our circle from 0 to 2 pi. Given we know mu naught, we know our current, and we have the other components. And from here, it's just plug and chug. This one is really nice because everything else is constant, and we can pull out most of the fraction to the front of our integral and just integrate d theta in our k hat direction, which just ends up being 2 pi. So it makes some nice cancellations for algebra, but these problems are pretty straightforward. It's just remembering how to find your R vector and your DL. Most of the rest of it is just algebra. So any questions? Wait, oh, I did get a chat. On exams, we wouldn't need to go through all of this since we have the B current loop equation, right? Tyler or Nick, do you want to speak to that?
absolutely, yeah, no. You definitely don't have to go through that process because you do have the equation sheet. I just think it's sort of helpful to get an idea of how it's derived from the Biot-Savart law. And the reason why I think I chose that one is because it's just sort of like the most you can see at once. Like you won't see a Biot-Savart law problem harder than that one, I can say with pretty good confidence, because that one like had everything. It had your point was off the center of the circle. It was some distance z above, and then there was just a lot of moving parts, but I think it's helpful to see how it sort of fits into place. But no, definitely don't go through that on the exam. Save yourself the time and look at the equation sheet.
Awesome. Thanks so much, Portia, for going over through that problem. I'm not a huge fan of the Biot-Savart law, so I really appreciate that.
Yeah, for sure.
Yeah, thanks so much. So in this case, next we saw the magnetic torque and specifically the slanted wire problem. People wanted to see next. Actually, you're unlucky because that is the example that we did pick. And I will say it's a very good choice because this was, Nick, correct me if I'm wrong, this was the exam problem last semester, was it not? I want to say, I think so.
I think so.
Yeah, right. Yeah, I remember it was a pain and grade, but yes, so this problem does come up quite often. It makes a very good free response question. You can tell when something makes a good FRQ when it has multiple parts to it, as in like solving for an R vector, solving for a DL, things like that, right? So those types of problems make good FRQs. So I wouldn't be surprised to see this one on there. So I do appreciate you guys asking about this. So without further ado, we'll go through it. So we have this lovely current carrying wire, right, on the XY axis. It says it's free to rotate about the Y axis here, right? In the presence of a uniform magnetic field equal to B naught J hat, right? So B naught in the J hat direction, right? So we want to know what the torque on this wire segment would be, right? Given all these variables and things like I and R vectors, things like that, right? So first thing to realize is that it is free to rotate about the Y axis, right? So that should tell you that the important variable, or the variable we want to have everything in terms of, is X, because X is perpendicular to Y. Right, remember our torque expression in general, right, is an R cross DF looking thing, right? And if my R vector is in terms of Y, right, and my force is in terms of Y, well, that's just two parallel vectors, right? So in this case, I want to make sure that everything is in terms of X because that is perpendicular to my Y axis, right? So that's just a quick little initial thought here that we're looking at, just so you can see that and say, okay, well, I know where I want to go, right? And in fact, that is kind of what we've got on the next slide here. So our strategy generally, all right, we're going to find a magnetic force first, the differential force in this case, right? We can't make that simplification that everything's constant because I do have to integrate over that entire length of wire, excuse me. And then from there, right, we got to do the other half, right? We got to find the R vector, and then we can cross those two to get the differential torque. And then we can integrate that differential torque to find the total torque, right? So sort of that same general problem solving process will be followed for most of these torque problems, right? You're either finding R, you're finding DF, all these sorts of things, right? So yeah, like Portia was saying earlier, you can kind of go in any direction you want, right? I believe in this case, we start with our DL first, right? So that's where I will start, right? So here we are. So we know that the differential amount of force given by DF equals I DL cross with B, right? We already have the magnetic field, right? Life's good there. We don't have to worry about that. And in most cases, that will actually be the case, right? B field is usually given to you because you have to find a bunch of other stuff anyway, right? So B field's given to us, great. So all we have left to figure out in this DF expression, right, is that differential length, right? Because I is given as a constant, right? So we're good there, right? So DL, like I was kind of talking about earlier, right? There are many people that can go straight from nothing to a DL, right? I just don't work that way, right? So I always start with a length first and then go to a differential length just by taking a derivative. So that's what I'll do. But you can take it any way you want. This example does both, or example does the dx way. So let's start with length first, right? So remember, length just has to describe how I get from the origin or the place where my function starts to any point along that function, right? So I scroll back up to my picture here, right? Say I'm standing right here, right? And I want to get to, I don't know, some random point. I'll mark it over here in purple. I want to get to that point right there, right? So basically, how do I describe the path I would take to get from, well, where I started to where I ended up there, right? So notice I have to go some distance in the X direction, right? And some distance in the Y direction, right? X is, well, it's just X, right? It's pretty straightforward in this case, right? I'm not starting at some weird point. I'm just starting at the origin. So that means that any point I move along on the X axis is just going to be in terms of X, right? So I'll write it up here just so you can remember, right? Well, X I had to start with, right? And then in the J hat direction, right? I could say the same thing. Since I don't exactly know what function this is, right? I could just start by saying, oh, well, it's just going to be Y J hat in this first case, right? But remember my point earlier, we don't want to have everything in terms of Y because that is parallel to the Y axis. I'm going to turn that into a term with X in it instead, right? So trig is always a good friend of ours, right? So if I've got X here, got Y here, and I know I have some angle theta here, well, then I can write Y and X in terms of, well, a trig identity, right? I could say that tangent of theta is equal to opposite over adjacent. So Y over X here, for example, And I could solve for y to get it all in terms of x, right? So I don't have any sort of y's in my equation at all. Right, so I'm going to do that, and I'll say that I have xi hat here plus x tan theta j hat. Right, and now I've already eliminated my y variable almost immediately, right? I don't have to drag it around anymore. I've already eliminated it, so I don't have anything to worry about, right? So from here, right, I got my length. So from here, I can just go through and take my derivative of this length vector to get my differential length. Right, so that's where we'll pick up back down here, right? And then notice you still could have gotten here the differential way, right? I just, like I said, my mind doesn't think that way, but you could have gotten there just by saying dx dy and then solving for dy the same way we solved for y in the first case, right? So either one would have worked, right? But I'll rewrite that here, xi hat plus x tan theta j hat. Right, and then the most important thing to remember when you do it this way, however, is that remember x is not a constant, right? X will change as I move along my wire from where it starts to where it ends, right? So see a lot of people that want to just take the derivative of x and just say, hey, it's 1, right? Well, if x were constant and we knew what it was, sure, the derivative of x would be 1, right? But since we don't, we have to take an implicit derivative. So for those of you who don't remember, it is just going to be dx there, right? Implicit just means I don't know what that variable is, or I don't know exactly what it is, so I'm just going to take the derivative and leave it as at differential form, okay? So same thing for x tan theta, so I'll just get tan theta dx j hat, right? Sorry, I kind of ran out of room there, right? But just the derivative of x tan theta with respect to x, again, in that differential form, right? So either way, we would get to our DL get to the exact same answer on our DL, right? Just 2 different ways to do it, right? So no matter what, that is our differential length vector. All right, so we're pretty good there. So now we have all the constituent pieces of our DF, don't we? Right, we got DL, we just found it. B was given to us, and so was I, right? I was given to us. So from here, right, we can either put that to the side or go ahead and take the cross product now. Either way you want to do it. I believe this example goes to the cross product first, which I would recommend just so you don't, I guess, get caught up in how many different equations you have for different things, right? So from here, right, again, there's that DL expression, right? And we will take the cross product of this sucker, right? And I'm going to be honest with you, I haven't done a cross product in like 2.5 years. So I'm glad Nick put it on here for me. It's just going to be B naught dx in the k hat direction. Right? And if you need some help with cross products, I'm sure we can help you out with that. But I won't go through them here. In this case, I will just say, hey, cross product is B naught dx in the k hat direction. Right? And that makes sense, right? We're crossing an I and a j hat component with another j hat component, right? So it makes sense that I only have a k hat come out of that, right? So life's pretty good now, right? I got my DF is just going to be, well, what I just got, right? Whoops, that's an eraser. All that multiplied by my current, right? Because that's the only variable I have left to deal with, right? So all in all, my DF is I B naught dx in k hat direction, right? So from here, right, I'm about halfway done, right? I've got half of my torque expression, right? I know that torque again was R crossed with DF. Sorry, guys, I don't quite know what happened there. Give me 1 second. All right, can everybody hear me now?
Yeah.
Awesome. Thanks, guys. Sorry about that. I don't really know what happened there. I had to stop my own screen sharing. It was annoying. All righty. 1 second. iPad just crapped itself out of nowhere. Sorry about that. Cool. All right. Where did I cut out randomly? Did I get to, I guess, to this differential force part?
Yeah.
Right after I said DF. Awesome. Cool. Thanks, guys. Appreciate it. Sorry about that. So just to backtrack just a bit, just me talking randomly into space. After we've got DF, right, I can remember my torque expression, right? Differential torque is radius crossed with differential force, right? So after I've got that force there, right, life's pretty good, about halfway done with torque, right? So I need to now focus on the R vector, right? And then similar to what Nick was saying earlier, it's actually a very good point that I forgot about, is that this R vector right here, right, is not the same one that you might be used to from Phys 2, right? That R vector is not describing how I get from the source to the point, right? This is describing the radius from my axis of rotation, right? So this will be a Phys 1 interpretation of this R vector, right? So what that means in this case of this problem, right, is if I want to find the torque about the y-axis here, right, then my R vector has to start wherever my axis of rotation is, right? So in this case, the y-axis, and has to point to the point, or to any point along my wire, right? So again, entirely different from the R vectors that we might be used to in this class, right? Just a different definition, but they're still vectors, right? Just describing the locations of which might be different, right? So again, just remember the difference, right? In torque, we're talking about from the axis of rotation to whatever is, rotating, right? And then in the BO sub R law, it's whatever's making our magnetic field to wherever is experiencing our magnetic field, right? So very subtle difference, right? But pretty important, because in this case, you would get the opposite sign of what would actually be the case if you used the incorrect version of the R vector, right? So just something to pay attention to. But in this case, I've drawn it for you right here. So R vector, right, from axis of rotation, I believe is abbreviated as AOR from Phys 1, right? So I will start here on that axis, and I will go towards some point on my wire. Now I have to describe this vector in terms of, well, variables and things that I know, right? And so similar to kind of the length vector where we started down here, right? My R vector is only going to have one component because it's a horizontal line, and all I've got is x I hat. That's all I got, right? There is no vertical component of my R vector because it's all from the axis of rotation, right? All straight over to the right, right? And then I can describe it just in terms of x because, well, I'm starting at the origin, right? Or starting at a place of 0x, right? So origin 0x, same sort of thing in this case, right? But that would be how I would get to my R vector in this case. All right, so I'll stop here very briefly. Does anybody have any questions about about the difference between this R vector and the BO sub R law R vector, or I guess how I got this, how I came up with this, anything like that? Cool. I'll take that as a no. That sounds good. All right. So where were we, right? So on the slide above, right about there, all right, we had established what our differential force vector was, right? We got that, right? So it's just written out for you right here again, right? And then similar to what I was just saying, right? We solve for the R vector next, right? Again, points from the axis of rotation to the point where the force is being applied on the wire, right? So in this case, it'd be straight to the right. Okay. Again, just remember the difference between the R vector in these problems and the R vector in the BO sub R law problems, right? Very, very different, right? Although they might look similar in certain cases, right? So just make sure to be mindful of the difference, right? But now the good news is once we have both these components, right? I've got DF and I've got R, I can just cross the two, right? And come up with my differential torque formula, right? So in this case, my cross product becomes much, much easier because I've only got, well, two variables or two components to worry about, really. I got nothing in the j hat direction, period, right? And then some zeros here and there in the I hat and k hat directions as well, right? So all in all, you end up with a pretty straightforward cross product, right? It's just the multiplication of those two components, right? So we end up with negative I b naught x dx in the j hat direction, okay? So again, just another straight up cross product there. If you have any questions about that, please feel free to ask, but if not, I will not go through that cross product. So now, once we're here, we're about 98% of the way done, right? From here, usually the integration in these problems is the easiest part, right? I find more often than not that I make mistakes on the cross product more than anything else, right? Cross product and the differential length / radius vectors, things like that, okay? So the integration is usually pretty straightforward, right? And it tells you what to integrate with respect to because I've got that variable right there. I have that differential x, right? So I know I must be integrating with respect to some x value, okay? And because of that, my bounds have to reflect 2x distances, right? So I can scroll back up to my picture here and I can figure out what those x distances would be, right? After I erase some lines here, just make things a little cleaner, right? So I already established that I'm starting at the origin, right? Or the start of my wire, right? And then I'm going until, well, the wire ends, right? The wire is going to end about, well, about there in the x direction, all right? So the problem is I can't just say that's 0 to L, right? Because that's not the total length, but the total length is, well, that distance right there, right? That would be L, right? So I don't have L, but I have some component of L, right? So handy dandy trig, we'll say that is L times the cosine of theta, right? So that would describe my total length in the x direction. Therefore, that is what I will use in my upper bound, right? So as you can see, be right about there, right? Again, I start at the origin, so it's going to be a fat 0 right there. Now integrate to L cosine theta, because that is where that wire ends in the x direction. All right. Keep in mind here, it's easy to mix up the bounds if it's talking about the torque in the across the y-axis. Might be tempted to say, oh, well, it's L sine theta because I'm talking about across the y-axis. Well, you're talking about torque across the y-axis, but I only have so much wire, right? I'm talking about the amount of wire I have in the x direction, right? So that would not be representative of what I'm asking, right? So again, got to make sure that the bounds and the differential variables, those should agree on their distances, okay? So put that all together, you will get negative, all this stuff, right? In the j hat direction, right? What would theta be? Lisa, it's a good question, but what do you mean? Theta is a variable, so what do you mean? I guess theta is just a value of some angle, right? It wasn't given to us in the problem. Yeah, no, you're good. You're good. Yeah. So really that theta again is just dependent on, or really how much torque we get, right? Is dependent on, well, the angle of that wire off of the x-axis, right? Because you're going to get different values based on different, theta values, right? So that's all that's saying. But more often than not, it will just be given to you as a variable theta. So don't worry about that. Okay. All right. Other than that, I've talked for long enough. Does anybody else have any questions? If not, I will pass it off to Nick for the inductance and RL circuits question, because that was the next most popular one. Everybody all good? Sorry about me being muted randomly there. That was my bad, but I think we should be good to go. Oh, we got one more. Cool. So it's just the j direction because it's rotating about the y-axis. That's a good question. So Kaylin, I believe that this was more of a, the fact that this is in the j hat direction. I can't remember if this is enough of a, I don't remember torque well enough from Phys 1, if this is a coincidence that it's in the j hat direction, or the fact that it's fact that it's across the y-axis means it's in the j hat direction. I can't remember that for sure. But I would say that whenever you take the cross product, you will end up with the right component, right? The across the y-axis just means you had to put your r vector in terms of the variable going across the y-axis, right? Because remember we started with that. Right. So the axis of rotation will be taken care of in your r vectors and things like that beforehand, right? That j hat is as a result of that cross product. Cool. All right. Nick, you there, buddy?
I'm here.
Cool. All right. I will pass it off to you for the inductance question. All right.
All right. Sounds good.
Cool.
Let me share my screen.
And Nick, I will be right back. So if you need something, I will not be here.
Of course. Cool. So let's do an inductance problem. Okay. Let's do this one, the solenoid through a coil. So what we have here, and I don't think you guys had access to this problem in long kappa, so this is just something I came up with, but we have a long solenoid of length L, 18.5 centimeters, and it has 25 windings through a cross-sectional area of A, and the solenoid is going through the center of a circular coil of wire, so that's that one of radius B, and the current in the circular coil changes according to I of t is just this function. And this problem is telling us to find the magnitude of the induced EMF in the solenoid at t equals 3 seconds. Cool. So the sort of hints I have to use mutual inductance is just the fact that I have two coils. And whenever I have two coils, there's gonna have some mutual inductance between the two. Why can't I scroll? Oh, cool. Figured out. Okay. Yeah, so all I have to do here is start by finding the mutual inductance of these pair of coils. And then I can use Faraday's law to determine the induced EMF in the solenoid at some later time t. So again, it's a mutual inductance problem. Just because I have two coils, there's nice symmetry between the two. And there's some nice approximations we can make such that I can easily make statements about the flux in one based on what's going on of the current in the other. So let's work through it. So on the equation sheet, the equation for the mutual inductance of a pair of coils is given as M is the number of turns in one times the flux through that coil divided by the current in the other coil. And the nice thing about mutual inductance is that it gives us this sort of choice. We can either treat the coil as producing the magnetic field, and coils of course produce magnetic fields that, you know, with the problem that Portia did, they're sort of doing their own thing on the outside, and then in the inside, they're all sort of uniform. Or we can treat the solenoid as producing the magnetic field and finding the flux through the coil. So the alternative here would be that the solenoid is instead producing the magnetic field. So let's erase these. And the magnetic field produced by a solenoid is just going to be pretty uniform within the solenoid and pretty much zero outside the solenoid. And we can instead find the flux through the coil. Either approach works, but it's much easier to find the flux through the coil. Sort of just for the same reason that I gave, because if I want to treat the solenoid as producing the B field, well, that's my B field. That's all I have to worry about, because it's just pointing up within the solenoid. It's uniform within the solenoid, and outside the solenoid, the B field is pretty much zero. But I could hypothetically, on the other hand, instead consider the B field produced by the coil. But again, the B field produced by the coil is all sorts of crazy. Maybe it's sort of uniform in the middle, but it's sort of extending out and we don't really know what it's doing along the edges here. So determining the flux through the solenoid as a result of the B field produced by the coil is just a nightmare. Luckily, we don't have to do that because we can instead work the other way around. We can find the mutual inductance by considering the number of turns in the coil, the circular coil here, as produced by whatever is coming out of the solenoid. So in other words, what I decided I'm going to do, just because it's far easier than the other approach, is I am going to treat the solenoid as producing the magnetic field. It produces that blue magnetic field in the center there. And I want to determine the flux through this circular coil. So to determine flux, we just always start with the integral definition. Flux is the integral of B dot dA. And in this case, the area vector of the coil, that's just pointing straight up because area vectors point normal to the surface that they define. So the area vector of this coil, let's draw it separately here, is just going to be pointing up like that. And then we can say that the B field, that's just uniform and it's due to the B field of the solenoid. So the integral of B dot dA, since the B field is uniform and since the area vector is uniform, it's not like a curved area or anything. I don't really have to take the integral. I can just say that the flux is whatever the B field of the solenoid is times the area through one turn of the coil. And this is something that confuses a lot of people and definitely confused me. But we were trying to find the flux through the coil. We're trying to find the flux through this large circular coil here that's bigger than the solenoid. But then why do I have this pi a squared here? Because if I go back to the problem statement, A was the radius of the solenoid. A is that radius right there, not the bigger radius B, that's the coil. Well, the reason why I'm using A instead of B there is because the magnetic field produced by a solenoid is 0 outside of a solenoid. So even though I'm trying to find the flux through this whole entire circular coil shape, the only portion of the flux that I care about is the portion contained by that area of radius. I guess it's the area of the solenoid, the cross-sectional area of the solenoid, and the solenoid had radius A. So the area that I care about is pi A squared, even though the area of the coil is pi B squared. That's definitely a touchy point, so don't hesitate to post a question if that didn't make sense. Cool. So then the mutual inductance, all I have to do is take the number of turns in the solenoid, take the number of turns in the coil and sub B, multiply that by the flux through one turn of the coil, that comes from the B field of the solenoid, times the area of, again, it's the area of the coil that we're considering, but the only area that matters is that smaller area pi A squared. And I have to divide that by I solenoid, or the current in the solenoid. Those two cancel, and I get this nice expression. And this sort of just reaffirms the statement I made earlier about how mutual inductance is a little bit comparable to capacitance. Because capacitance, it never depends on charge or voltage. It only depends on the geometry of the capacitor. Same thing here. Mutual inductance, it only depends on physical constants like mu naught, and then constants like the number of turns or the length of the solenoid or A squared. It doesn't depend on currents or voltages or EMFs or anything like that. But we're not done yet. We have the mutual inductance, but the problem was asking us to find the induced EMF in the solenoid. So to find the induced EMF in the solenoid, I take the flux in the solenoid, and then all I have to do is take a time derivative, because Faraday's law, again, Faraday's law says that the induced EMF is the negative time derivative of the magnetic flux. And the magnetic flux is just the mutual inductance times the current. So if I take the derivative of this quantity, the mutual inductance doesn't change with time, so I don't really take its derivative. But then I'm left with di dt. So I have to take the derivative of the current in the coil if I want the induced EMF in the solenoid. And luckily we have a function for the current in the coil. So the magnitude of the induced EMF in the coil at some later time t, I just apply this formula. It's asking for magnitude, so I just drop a negative sign there, but that's again harking back to Lenz's law. And I can plug in whatever time I want. I think I wanted 3 seconds here, so that's where I have it. I think the nice thing about mutual inductance problems is that they often appear super scary at first. Like we had the graded group activity a while ago with the macaroni loop or whatever, and it had the solenoid going through it. And I think that problem looks scary, but it's really not too bad when you get it into the meat of it. All right, what did I say that does make sense? What needs more clarification?
Evidently nothing. Seems like that's pretty good, Nick.
Awesome.
Cool. Awesome. Well, it's not 8 o'clock yet, so we'll just keep going right with the survey anyway. The next question people wanted to see most was Ampere's law. Seemed like there was a lot of votes for that, so we do have one question on that. So I will go ahead and cover that. But after that, it's free roam for questions after that. So if you guys want to just pop in and say or ask anything you'd like, we'll be happy to answer that for you. But until then, going to go over that Ampere's law question. All right. Come up in just a second. Awesome. Cool. All righty. So yeah, this should be just after your Ampere's law notes in the document you're following on. Right. So we're trying to use Ampere's law to solve for magnetic fields in this kind of weird concentric cylinder looking scenario. Right. So if this did happen to be a free response question, it would look something a lot like this, right? It might not have 4 constituent parts that it wants you to find a magnetic field at, right? But it will definitely give you a non-uniform current density. right? So you have to integrate to find the current, right? Because that's the whole trick, right? And then it will ask you for a magnetic field at usually a couple different distances or maybe one specific distance in terms of variables, right? So that's what we're going to do, right? So with this cylinder, we're talking about a wire with radius A specifically carries this amount of current I naught, right? So that means just this circle right here, right, carries some amount total current of I naught, all right? And we're saying an annular cylinder with inner radius B and outer radius C is concentric with the inner wire, means just centered on the same spot, and carries a current such that its current density is given by that current density right there, right? So this problem is actually a bit of a curveball because we have two different variables to worry about, right? If I am inside this radius A here, right, well, then I've got some value for current, right? And if I'm, well, outside radius A and inside radius C, then I've got some other value, and I got to have a current density to worry about, right? So again, Nick's point earlier, we pick examples that are usually much more difficult than you see in the exam, but the problem solving process is the exact same, right? So we'll go ahead and go through it. So the structure of how we solve this problem, we are going to solve for the current through all of them first, and then the magnetic field after that, because the magnetic field step is all the same, right? So we'll solve for current first and then magnetic field after that. Okay, so that's the structure here. So first one, right? First part A, want to find the magnetic field or the current for a radius less than A, right? So less than that inner cylinder A, right? Where we're somewhere in there. We want to know what the current is or the magnetic field is at that point, right? So again, like Nick says, right, where each of these we'll need to calculate the current enclosed first, right? Because that's always our hardest step. And then from there, we can simplify Ampere's law and actually solve for a magnetic field. So without further ado, we'll look at part A first, right? So there's a lot going on here, but it's okay. We'll go through it. So part A says, again, for R less than A, right? So we're trying to find the current enclosed by the Amperian loop that is confined to the inner conductor, right? So again, R less than A, where the current is uniformly distributed in this case, right? Remember, we were just given a value for it. It was I naught, right? So we're trying to find the current, the ratio of the current that we've got, right, inside that radius, right, given the fact that the current is uniformly distributed, right? So we can start with the formula for the current through a loop, right, something, or a cylinder, something like that, right? It would be the integral of J dA, right? So J, we established in this sentence here, that by definition, it's the total current, right, divided by the total area of the shape that holds that current, right? So in this case, if I just have that one circle with radius A, right, well, then my total area I know is just pi A squared, right? And it gave me the total current, it's right there, right? So J as a definition, right, is going to be right there, I naught over pi A squared, right? And since that current is uniform, right, we just pulled it out of the integral, right? Now we just have the integral of dA, right, which we know just becomes A, right? But it's a little different in this case because we're at some radius less than this constant value, right? So you can look at it that way, or you can actually plug in the values for differential area, right, which would just be the derivative of area, right? So 2 pi r, we use r prime as a sort of a dummy variable. They use that in Phys 1. So just a dummy variable just to differentiate it between this bound, right? So we'll integrate that area over those bounds from 0 to r, and we will end up with this neat ratio of the areas multiplied by the current, right? Which makes sense, right? The current is uniformly distributed. That means J will be the same everywhere, right? So it makes sense that I would have that ratio. That ratio's got to hold consistent, right? So for R less than A, right, this is my current, right? The ratio of my current, right, for R less than A, okay? Any questions about that first part there? There's 3 more, but just check and make sure that this one makes sense, just the first part. Cool. All right, I'll move on to part B, all right? So part B, a little different, all right? Now we're talking about radius A less than or equal to R, less than or equal to B, right? So a little reminder, right? We basically had this situation, right, where that's a terrible drawing, but I've got current there and current here, right? And this region here in purple, right, this is all empty space in here, right? There's nothing there. All right, so I'll just erase that so it's not getting confusing, but there's nothing there, right? So what that means effectively is that whenever I'm outside radius A, but not quite to radius B, I have all the current in that first radius, right? I have all of it, right? So you can go through the mathematical steps to prove it to yourself that the through current is just I naught, right? But
it also told you in the problem that through radius A, you just have that total current I naught, right? Going through that radius, right? So you wouldn't have to do any of this if you didn't want. You just say, oh, well, you told me the total current going through radius A was I naught, so I through is equal to I naught, right? Either way, but say you did want to prove it to yourself, right? I'll stick with the same J, right? Current density, right? I naught over pi A squared that we established last time, right? That dA term still remains the same, right? The derivative of area, but now my bounds, I've got all of that inner radius, right? So it would be from 0 to A now, right? Not from 0 to R, right? Like before, right? 0 to A, because I'm outside that radius A, right? So I need all of the current that's there, right? The only place where I could see some confusion here is keep in mind that I'm integrating to find current here. So it doesn't make sense for me to write B here, for example, or R or anything else, right? Because I only have as much current that is enclosed by this loop, right? So there's no current, see in blue, there's no current between my Amperian loop and my radius A, right? There's nothing there. So I have to make sure my bounds reflect that. My bounds can't go from 0 to R, right? Because that would give me more current than I initially bargained for, right? I only have 0 to A, right? Because that's all the current I have enclosed. Okay, so just make sure your bounds should agree, right? And it actually says it right here, I got to lie on myself, right? Should indeed be the case that the current through the Amperian loop is just the current carried by the inner wire, right? You don't have anything else, right? You're not enclosing anything else just because you're outside that radius, right? You have still that same amount of current. Okay, so again, for A less than or equal to R less than or equal to B, right? I is equal to I naught. Okay, that one's fairly straightforward there. I feel like that one's pretty intuitive for most people, right? Not too many complicated things going on there. All right, but any questions on part B? Cool, take that as a no. All right, so now move on to part C. All right, we start to get a little more complicated here because my current is not uniform anymore, right? I still have that value, right? Because I'm outside that radius, right? But I've got a current density now, right? It's telling me that the current is changing as I move through an area apart from radius A, right? So in that radius, in that region where B is less than R less than C, right? So again, just a reminder, that looks like anywhere inside of here, right? Just a little reminder, right? Where that had some, that had some current, and all this has some current as well, right? So you can see how these problems are very nicely scaffolded, but we're trying to find the amount of current enclosed by that purple loop in there, in between radius B and radius C, okay? So we'll put together the same sort of integral, right? Don't forget about this I naught term, right? Because we do have that current there before, right? We didn't lose it, right? We're just moving further and further away to encapsulate more current, right? So don't forget about this, right? That doesn't go away just because you move further and further away, right? It is just now an addition, right? We don't need to integrate anymore because we already did, okay? But notice this integral of JDA should look a little familiar, right? Except the J is now that non-uniform current density, right? It shouldn't be the same as my radius A, right? Because I'm not talking about that radius anymore, right? I'm talking about in between B and C, right? So I've got a new current density, 1 over R squared, right? But notice my dA term, because I didn't change the shape of my Amperian loop, that dA term is going to be constant all the way through. I've got the same area every time I talk about one of my Amperian loops here, right? Because it's all a circle, right? So that's nice, right? My dA is always going to be the same, right? 2 pi r prime or r, whichever one you choose, dr. Okay, so I can put those two together, multiply them together, and I end up with just dr over r prime. So right here, right? One of the r's cancel, and I can pull the 2 pi out of the integral, right? Life's pretty good. And then hopefully you guys remember that the integral of 1 over r would just be natural log of r, right? And so we'll plug in the bounds from r to b, right? We'll end up with this nice expression for current in between b less than or equal to r equal to c, right? So I would say that one's fairly complicated just because you got a natural log to worry about, right? And sometimes we forget what the integral of 1 over r might be because it's not a super intuitive one, right? But yeah, so as long as you remember the integral of 1 over r, that one's pretty straightforward, right? Not much of our rules changed, just the fact that we had a non-uniform current density changed. That was it. Everything else stayed exactly the same. Cool. Any questions on part C before we move on to part D? Cool. All righty. So part D, the very last part, right? Now, the only place we've got left to check for the current, right, is when R is greater than C, right? So at this point, I have it all. I've got everything, right? I have all the current in my entire concentric cylinders. I got everything, right? So again, quick recap. If I draw another terrible picture, I am now way out here in the boonies. I've got all my current enclosed in this loop now, right? So at this point, right, my integration becomes pretty trivial, right? Because I've basically done this twice now at this point, right? Don't forget about your I naught again, right? Well, df, don't forget, right? And then my integral is exactly the same as before, except now my bounds change to reflect the amount of current I now have in my Amperian loop, right? So again, I only have as much current as present in my entire loop. So I can't have from B to R, for example, right? Because that would give me more current than I bargained for. I can only have current up until radius C, because that's the edge of my entire cylinder, right? So again, that's really the only place where I see people start to make mistakes is the bounds there. But remember, again, this is a current integral, right? I can't have more current than is in the system to begin with, right? So those bounds should always reflect the actual geometry of my system, okay? But that being said, right, J remains the exact same, nothing changed there. And like I said before, dA is, well, still unchanged, right? I've still got a circular Amperian loop, so that dA will not change at all, right? I can pull that 2 pi of my integral, and so I have the integral of, well, basically 1 over r again, and so I'll get that same natural log form, right? Except now it's going to be natural log of C over B, right? Because those were my bounds, not R over B, right? Very, very subtle difference there, but keep in mind I've got all the current in my entire cylinder now, right? So not R, C. Okay, so this would be my current for R greater than C is equal to that sucker right there. Okay, so at this point, this seems like a lot of work, but I promise we basically just done the same thing 4 times, right? At different radii, right? And so what follows is the exact same problem solving process for each part, right? We solve the right-hand side of Ampere's law, right? Which is the mu naught times current through form, right? Current through, right? This is the only thing that would change, right? For each, well, I'd probably just say that, right? That value is the only thing that's going to change depending on where I'm at in my cylinder, right? The path integral of B dot dl, right, for any circular path is always going to be the exact same, right? So we follow this problem solving process, right? Those vectors are parallel to one another, right? B parallel to dl, right? That leads me here, right? B field is constant, so I pull it out of my integral. That leads me to that 3rd step there, or that 2nd step. And then finally, I can plug in just the length of my Amperian loop, which for a circle should just be the circumference of my loop. All right, so I have B just times 2 pi r. All right, this is going to be the same for A through D, right? Because my loop didn't change, right? I've still got the same Amperian loop, right? Its radius just changed, right? But since this radius is my variable that I'm concerned with anyway, right? 2 pi r is just constantly just 2 pi r, right? Nothing fancy going on there. Should always just be 2 pi r. Okay, so the next 4 slides are just us plugging in this 2 pi r over here and then moving it over, right? So it's I mean, it's literally a simple division. That's it. But yeah, there's 4 slides for that, just so you guys can see the different effects that finding the magnetic field at different radii, what that ends up looking like, right? Because a lot of these questions will seem familiar after a certain amount of time because all the shapes are very similar to themselves too. So again, we solved for them all here for you, right? Notice that is the B field made by an infinite wire, right? That is found on the bottom of your equation sheet, right? So don't forget about that, right? That is a very, very useful formula, but know that it came from Ampere's law, right? So, all right, other than that, yeah, like I said, we're just plugging in 2 pi r here. So we'll just keep dividing, and yeah, that's pretty good. All right, so at that point, our problem solving process is done. We've got the B field at 4 different places in our current carrying wire. Does anybody have any questions after that? Cool. Take that as a no. I find that Ampere's law, once you kind of do a few problems through these scaffolded problems, they usually starts to come pretty easily to you. The problem solving process is really not any different than Gauss's law. You're just dealing with DLs instead of DAs, right? So hopefully that covered that question for you guys pretty well. Other than that, it is about 8 o'clock, so that concludes our like scripted review session necessarily. So for those of you left, you're more than welcome to stay. Ask us anything you'd like that's not necessarily given to us here. But yeah, feel free to unmute or type something in the chat if you'd like, because that is all the scripted material we've got, though. Thanks, guys, for coming.
Thanks so much. We really appreciate it.
Not a problem, guys. Not a problem. Good luck in the exam on Wednesday, all right? Nick, I don't know what's going on with your camera, man. That's super weird.
My camera's all sorts of crazy. Do you like my background?
I do. It's funny because I see your face half the time, and then I see
Yeah, yeah.
Harambe's or whatever gorilla that is the other half the time. You're teleporting all over the place. Like you got a rave or some shit. Pretty funny. Ooh, Nick, you got a transformer question. I know you love those.
I got it. Can we go over the transformer question of the 2017 exam? Yeah, let me pull that up real quick. 1 kappa.mines.eu. All right, let me start screen sharing. Screen share. Screen share. Whoa. Cool.
Sorry, I just had to unmute and laugh at that, Nick. I love you.
No. All right, where was that? That's in block 3. 2017. Then transformers. This one. Let's see. Nick, do I know about the 2011 FRQ? We can definitely go over the 2011 FRQ after this one. Is this the transformer question that you meant from the 2017 exam? Okay, cool. Yeah, let's do the transformer question real quick, and then we can do the 2011 FRQ, if that sounds good to people. Cool. Cool. All right, so it says, the picture below shows a crude transformer, a device for transferring energy from one circuit to another. So what we have is solenoid 1, which is wrapped tightly around an iron bar, meaning that any magnetic field produced by solenoid 1 is going to be transmitted exactly down to solenoid 2. So what we're going to do is we're going to pass a typical household current through solenoid 1. Let's say I of t is equal to I naught sine of omega t with frequency of 60 Hertz and 1 amp I naught. The solenoids are each 3.5 centimeters long. Calculate the maximum voltage that will be induced in solenoid 2. Okay. Cool. So the equation, or let's see what we want to do here. So we have a transformer, and if it only zooms annotate. Can I pull up a different whiteboard? Let's just go to an empty page here. Or no, that's not gonna work. Sure, sorry. Okay, I'll just use zooms annotate. Okay, so what we have are 2 solenoids wrapped around an iron core. And that means that whatever B field I have in one is going to be transmitted directly to the other. And moreover, what that means is that if these 2 solenoids, they both have the same number of turns, 160 turns, and they're both wrapping around the same iron core, which means they have the same area. More than them just having the same B field, they also must have the same flux. So flux, again, is defined as the integral of B dot dA. And this tells us that if the area is the same, and they are because they're wrapped around the same iron coil, and they have the same number of turns and all that, these 2 coils are going to have the same flux, which means it changes with time the same exact way. So let's say the flux, let's make coil 1 the red coil, and coil 2 is going to be the blue coil. So then what we can say is that the flux in coil 1 has to be equal to the flux in coil 2. And moreover, what that implies is that they both change with time in the same way. So if I take the time derivative of that equation, I will find that the induced EMF, which is the derivative of flux of coil 1, is going to be the same as in coil 2. So by virtue of having the same area and the same B fields, they have the same flux and hence the same induced EMF. So what does that do for us? Well, that tells us, first off, we want to calculate the maximum voltage that will be induced on solenoid 2. And if I want to calculate the maximum voltage on solenoid 2, wait, solenoid 2 was the blue one, my bad. Undo that. Let's go here. So the maximum induced EMF of coil 2 of solenoid 2 is going to be this quantity by Faraday's law. Just the derivative of the magnetic flux. But I know that that quantity is equal to whatever the derivative of the flux is in coil 1. So that has to be equal to that. And what that tells us is that I guess you don't even have to have them having the same number of turns, because I guess a more general form of Faraday's law is rather than just having the derivative of the flux out here, I would have N2, because what I'm doing is I'm really multiplying the number of turns in solenoid 2 times the change in flux through solenoid 2. That has to be equal to N2. I carry that factor out in front, but then I can interplace this quantity with what it's equal to. I know it has to be equal to the flux through the other coil. I can replace that with that right there. And that's really nice because I can recognize this. Or rather, I can sort of do a similar thing for solenoid 1. I can say that the induced EMF in solenoid 1 is just going to be the number of turns in solenoid 1 times the flux through solenoid 2, or the change in flux in solenoid 2. And that gives me the relationship that's so handy with transformers. It's the, I think the colors do help here, so I'll stick with them. The number of turns in solenoid 2 times the flux in solenoid 1 has to be equal to the number of turns in solenoid 1, solenoid 1 times the flux, or excuse me, times the EMF of solenoid 2. Did that little mini derivation sort of make sense? And Tyler, I don't know if you're still here, but if you have things to add. Oh, you're here, you're cool. All right, what, okay, cool, that makes sense. Awesome, so that's exactly what I have to use. And now I can actually go to solving the problem. It says calculate the maximum voltage that will be induced in solenoid 2. So using this equation for transformers, the maximum voltage in solenoid 2 is just going to be N2 divided by N1 times the maximum induced voltage in solenoid 1. So if I have a maximum here, then I must be taking the maximum here. Conversely, I could also be looking at RMS values for the voltages, but right now it's wanting the maximum value. Cool, so both of them have 160 turns, so 160 divided by 160, that's just 1. And basically this tells me that the maximum induced voltage in solenoid 2 is just going to be the same as in solenoid 1. So if I go here, shoot, let's see. Calculate the maximum induced voltage. I thought for this one, we don't use the equation with the ratios. You might be right about that, because I'm at a dead end with this one. Yeah. Let's see. Solenoid 1 has 160 turns.
Yeah, Nick, if it helps,
Yeah.
all you have to do is just the Faraday's law with magnetic.
Okay. So I went through that whole derivation for nothing.
No, the derivation definitely is good to know that, but that's only if
Okay.
you know
Okay.
EMF.
Cool. My bad.
Yeah, I came
Thanks for
to
your
that same conclusion earlier. Don't worry.
Thanks for your input. Okay.
For sure, man, for sure.
Yeah, so note that the equation made for the magnetic field on a solenoid. Okay. So the magnetic field of a solenoid is B is equal to mu naught lowercase n times I. So then the B field made by solenoid 1 is going to be mu naught times the number of turns of solenoid 1 divided by its length times I of t. Yep, okay. I just went for this whole thing for nothing, but that's okay. I of t, which is equal to mu naught n1 divided by L times I naught sine of omega t. Cool. And if that's the B field in solenoid 1, it's a transformer, which means they're wrapped around the iron core, which means any magnetic field produced by this solenoid will be in solenoid 2. So the B field in solenoid 2 is this exact same thing, which means that the flux in solenoid 2, if I clear some space for me and get rid of all this junk, cool. That's good. So that B field is going to be transmitted directly to solenoid 2. So the maximum induced voltage in solenoid 2 is going to be just what Faraday's law tells us it is, the derivative of the flux. And then that is just going to be the derivative of the B field, which we know from here. It was mu naught n1 over L I naught sine of omega t. That's the B field in solenoid 2. And then I have to multiply by the area of solenoid 2 and of course the number of turns. So N2, and the area of solenoid 2 is, let's get rid of that. The area of solenoid 2 is pi r squared. Cool. And when I take a time derivative, the omega is going to come out via the chain rule, and it's looking for the maximum voltage. So whenever I have signs and I'm trying to find the maximum of something, I can always just ignore all the sine and cosine terms, because sine and cosine, just as a function sort of by itself, is just going to be sort of oscillating between -1 and 1, -1 and 1. So it has just an amplitude of 1. Cool. So even though this sine, I am taking its derivative and it's going to become a cosine, I don't have to worry about that cosine. I do have to worry about the omega though that comes out. So we have mu naught n1 over L I naught omega times n2 pi r squared. Yeah, sorry for going through that whole thing for nothing, but hopefully that makes sense. Cool. And we wanted to go over the 2011 FRQ, right?
Yeah, Nick, so a little bit of context on that. I was looking at it earlier. It's that magnetic field of that slanted like exponential y or whatever the hell. But the problem is that on that 2011 exam, they asked for the torque in the last part instead of the actual magnetic field using the Biot-Savart law. So, but the main issue stems from the fact that the entire problem, I believe, is done in terms of dx, and that torque it can't be done in terms of dx. So we were confused as to whether or not we're supposed to convert everything to a dy after that and go from there, or what the hell they were looking for. So that question's your best guess, honestly, is what sort of like dx or dy they're looking for. And Lisa can give you some more context on that. But the problem's straightforward until that last part. Then I'm just not sure what exactly it's looking for. That's all I got.
So you worked on this earlier?
I did, yeah. Like I said, I'm
okay.
just not sure about the torque is all.
No, you're good. You're good.
Yeah, no worries. And I just want to say that unfortunately I do have to take off for the night, but let me know what you end up coming up with for the last part of this problem. I'm kind of curious.
Okay, for sure.
All right. Sounds good, man. Thanks so much for having us.
Yeah, no, thank you. All right. Yeah, let's sort of just